Welcome to homework.
So in this problem, we're going to have two cars colliding inelastically at a right angle. And we want to find what is their momenta compared to prior to the collision. And we're also given that both cars are exactly identical, meaning that they both have the same mass. So let's write that mass A equals mass of B. So if they're going to collide at a right angle, we can say that car A is going on the horizontal. And also, let's just keep in mind, our x's over here, positive to the right side and up. This is x and y. So we have car A going to the horizontal, and we're going to have car B going to the vertical upwards. They form a 90-degree angle, so right angle, and then they're going to stick together and they're both going to move in a different direction. So due to conservation of momentum, we know the momentum prior to the collision has to be equal to the momentum after the collision. So let's calculate the momentum prior. Now we have two different x's over here. So we have to take care of both dimensions. So let's start with the dimension x, and then the momentum, x initial, which is going to be, it's going to the positive side. So it's going to be mass of car A multiplied by the velocity of car A. And then here, we're going to have car B for them on the y-axis. So then momentum y initial, it's also going to the positive side. Therefore, mass of car A. Oh, sorry. Well, we could also say mass of car A. Let's actually, to make it simpler, let's just forget this A, and let's just say that all of this is just equal to mass. So momentum y initial is going to be mass times the velocity of car B. So then we know that when they're both stuck together, they're going to have these momenta are going to be exactly the same on these axes. So then we have over here, we can separate this final momentum into y and x-axis. This is vertical and horizontal. So we can separate over here as the momentum would be ma plus mb, which would just be 2m multiplied by the v final. Here, if we divide in both of these x's, we can see that v final is just going to be v final is going to be v final in the x direction plus v final in the y direction. But keep in mind, this is a vector addition, so it's not just going to be summing both of them. We're going to have to do the vector addition to find what is it. So then in the end, the momentum final in the x direction has to be equal to the initial momentum x final. So it is equal to mva, and then momentum y final is going to be equal to mvb. Therefore, vf is just going to be equal to vfx plus vfy, and we can separate these into x's, and we can get that for the y-axis we have initially mvb, and then here we're going to have it equal to this momentum over here, which is going to be ma plus mb, which is 2m, times vfy. So we can cancel out the m's, and we get that vfy is equal to vb over 2. Then over here, for the x-axis, we have initially mva, which then becomes 2m vfx. We can cancel out both m's, and we get that vfx is equal to va over 2. We can put the arrows here to symbolize these are all vector quantities. And we get both of these answers. So then if we plug it into here on the equation that we found earlier, we get vf is going to be equal to vfx, which is va over 2, plus vb over 2, or va plus vb divided by 2. Then let's say vf equal va plus vb divided by 2. If we say that va and vb have the same velocity, say that va is equal to vb in magnitude, then we will get that vf is just going to be equal to va, which is equal to vb, and we can call it just v. So then for the quantity of movement, or for the momentum, initially we had momentum for, if we say that the velocities are the same, for the x-axis we have mv, for the y-axis we have mv, And then after the collision, we would have 2 mv. If we sum mv and mv, we get 2 mv. And it shows us that there is a conservation of momentum in here. So the momentum is conserved prior and after the collision. The only thing that really changes is the direction that they're both going. The momentum in A is going to change. If we say that they're both the same velocities, is going to change 45 degrees, and for B, it's going to change 45 degrees. So if we have the same velocity over here, where this would be VA, and this would be VB, we would get VF, this number over here, and then for a 45, 45, 90 triangle, we get the VF, which is be equal to square root of 2 VA or VB, or just VF. So their momentums are conserved within their axis. And although they achieve a different velocity, both momentums are conserved, and the only difference that happens is that their masses come together and they share their velocity with each other, meaning that they pass half of the momentum to the other car. So B is going to pass half of its momentum to A, and A is going to move upwards, and A is going to pass half of its momentum to B, and B is going to move horizontally. And summing horizontal with vertical, we're going to achieve a diagonal movement with a velocity square root of 2 of the initial velocity. Let's just be over here, square root of 2. But their momentums in general are going to be conserved.